Hello, this is Professor Kuehn and welcome back to my Introduction to Astronomy. Today we're going to be starting into the work of Henrietta Leavitt. This is chapter 20 in a student's guide through the grade physics texts, and the chapter is titled The Luminosity of Variable Stars. Henrietta Leavitt did her work in 1912, that was the date of her most famous publication, at the Harvard Observatory. And this work ended up forming the basis of much of modern cosmology, as we will soon find out. But before we start directly into the work of Henrietta Leavitt, notice that we're taking a huge jump ahead in time. Last week we were looking at the work of Galileo Galilei, his Starry Messenger, which was published in 1610. Now we're going to be starting into the work of Henrietta Leavitt, which is in 1912, so we're skipping over 300 years. What happened during this interval? Well, as it ends up, quite a lot, as you might imagine. So what I'd like to do before we start into the work of Henrietta Leavitt and modern cosmology is kind of review where we've been and point out a few things that happened during the intervening time between Galileo and Leavitt. So remember that this course that I'm teaching is divided into three basic parts. The first part, you might say, is ancient and medieval cosmology. And I know it's hard to lump ancient and medieval cosmology into one topic. Of course, there are many different ideas. It's a very rich time period with many different ideas about cosmology. But one of the common themes was the idea of geocentrism. That is, the Earth is at the center of the world or the universe. And of course, as you learned, not everyone believed that. But that was a popular view. And that was really popularized, you might say, throughout ancient and medieval times by Aristotle, his book On the Heavens. Aristotle, you might remember, lived in about the 4th century BC or before Christ. So the first several weeks of this course, we studied ancient and medieval cosmology and geocentrism. Then we moved into what we might call early modern cosmology, which was really initiated, you might say, in about 1543 with the work of Nicholas Copernicus, his book on the revolutions of the heavenly spheres that we spent some time studying. I guess the most pronounced thing about early modern cosmology is you see a transition from geocentrism into heliocentrism. That is the idea that the sun is at the center of the world or the center of the universe. So we studied the work of Copernicus and Kepler and Galileo. Those are three of the most famous names associated with this early modern period. Now, in the last part of this course, the third unit of this course, we'll be moving into modern cosmology. And you might say that this is characterized by the idea that the sun is not the center of the universe. Rather, the sun is a star among many stars. And the star is a star in our own galaxy. And there are many galaxies or clusters of stars throughout the universe. This idea was really popularized by the work of the philosopher Immanuel Kant, who in 1755 came up with the idea of island universes. To be sure, he isn't really the only one who is thinking about this, of course. I think it was a man named Wright also was publishing things to this effect in the mid-18th century. But Kant is really the one who popularized this idea. And the theory of island universes says just that there are clusters of stars that we now call galaxies. He called them universes. And there are many of these galaxies throughout space. So he thought of these as island universes. Each galaxy or cluster of stars was a little universe that was an island, and then there's another one over here, another one over here. So now we would call these groups of stars forming galaxies, and these are scattered throughout space, and they're separated by enormous distances. So this is kind of the picture or worldview of modern cosmology that we'll be talking about over the next few weeks. So now what happened between the work of Galileo and these views of modern cosmology? Well, I want to point out a couple of really important things. And of course, there are many thinkers to choose from, but I want to highlight two of them, the work of Isaac Newton and the work of Freidrich Bessel. So let me write down the two scientists and philosophers that I'm going to be focusing on. So Isaac Newton. You have probably heard of Isaac Newton. He lived in England. He wrote a very famous book called The Mathematical Principles of Natural Philosophy. It's a long title. Today it's called the Principia or Principia, depending on how you want to pronounce your Latin. But his book, the Principia, was published in about 87. It went through a few different publications, so up to, I think the third publication was in 1703. So that's the time period. And just to remind you that Galileo published his Starry Messenger in 1610. So we're talking about, 90 years or so after Galileo that Isaac Newton published his Principia. Why was Newton's Principia so important? Well, in his Principia, he came up with what is now known as the universal law of gravitation. The universal law of gravitation, which claims that every object that has mass attracts every other object that has mass. So for example, if you have the sun, which has mass, it is pulling on the earth, which has mass. So there are these attractive forces that pull any two objects together. Likewise, the moon is attracted to the earth and the earth is attracted to the moon. This is the claim. Okay, now this is something you probably take for granted. You've been told this likely since you were very young, that gravity attracts the sun to the earth and the earth to the sun. But this is a very foreign idea. When he talks about gravity, Newton talks about it in a way that no one else was talking about it. The word gravity, to be sure, was being used throughout history, but by gravity, what was meant was kind of a terrestrial heaviness. That is, when you pick up a rock, that rock has gravitas or gravity. That's part of it. It's sort of a feature of that rock that gives it a tendency to fall down toward the earth. Likewise, trees have gravitas or gravity, so they fall toward the earth. So gravity was seen as kind of a heaviness things have that makes them move toward the earth. And more precisely, toward the center of the earth, or since the earth was seen to be at the center of the universe for much of history, toward the center of the universe. That's in fact the way Aristotle saw gravity. Now, that's very different than what Newton is saying. Newton is saying that that rock is attracted toward the earth, but the earth is also attracted toward that rock, and the sun is attracted toward the earth, and the earth is attracted toward the sun. Okay, and this is a very foreign kind of view, a very, very unusual view. It's a force of gravity acting between any two masses. And moreover, there is a law of gravity that could be expressed as a formula. So F equals, I'll write the formula down, G times the mass 1, mass 2 over r squared. So in this formula, this is the force of attraction. If you want to calculate it, what do you have to know? Well, you have to know the product, multiplied together, the product of the two masses involved. So that might be the sun and the earth, or an apple and the earth, or the moon and the earth. So those are the two masses. This r is the distance separating the masses, more precisely the centers of the masses. The distance separating the masses involved. And then we also have this capital G, which is the universal gravitational constant. It's a feature of nature, kind of like the speed of light or the mass of an electron. It has a value, by the way, in the International System of Units of 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. So if you're measuring the mass in kilograms, you're measuring the distance in meters, and you're measuring the force in newtons, well then this value of G is 6.67 times 10 to the minus 11. Okay? So it provides you a way of calculating the force between any two masses. How did Newton arrive at this universal law of gravitation? Well, it's kind of a long story, and we spend quite a bit of time in my Physics 151 and 201 classes reading through sections of Newton's Principia and showing how he demonstrates the law of gravity. So I'm not going to be able to go through all that right now, but let me just give you a hint of how he was thinking about this that allowed him to come up with his universal law of gravitation. So think for a moment about And this is an example that he uses in one of his scholia, or one of his meditations on the motion of objects. So think about the Earth for a moment. And let's suppose that there's a tall mountain on the Earth. And I'm just going to draw it up here. Okay, and let's suppose that you have a cannon that is aimed horizontally on the top of that mountain. Okay, and now let's suppose that there's a cannonball in the back of the cannon, and if that cannonball were to roll forward, it would simply roll out the end of the cannon and would fall straight down toward the Earth. Okay, so there's a tendency of things to fall downward toward the Earth, and that cannonball would simply fall straight down. But now let's suppose you fire the cannon. Well, when you fire the cannon, it still has a tendency to fall down toward the Earth, but in addition to that, you're giving it some initial horizontal speed. So it's going to fly forward, but it's also going to fall toward the Earth, and then it's going to travel a little bit farther, right? It's going to hit the Earth a little bit farther away. So there's this kind of dual tendency. The first tendency is by virtue of firing it, it's moving forward at a constant speed, and insofar as the air doesn't exert a lot of drag on it, it's going to continue moving forward at that constant speed. That's called the principle of inertia, by the way. But in addition, the Earth is attracting it, it's causing it to fall downward. So there's this combination of a principle of inertia carrying it forward, and then a force of gravity pulling it downward. And that's what gives rise to this trajectory of the cannonball. Okay? So you have the principle of inertia. I'll write these down. Principle of inertia. That's one ingredient. And secondly, a force of gravity that is causing it to fall downward. So that's responsible for the downward motion. And this is responsible for the forward motion of the cannonball. Okay? Now I want you to think about what happens, and this is exactly what Newton says. Think about what happens as you shoot it faster. If you shoot it faster, it's going to travel even farther, and it's going to fall, and it's going to hit the Earth. And I know this is a little bit unrealistic to imagine shooting the cannonball that far, but suppose you do that, and let's suppose you shoot it even faster, and what's going to happen as it's falling, the Earth is curving away from it, so it's getting farther and farther, until imagine if you fire it at exactly the right speed, it's going to be falling toward the Earth, but as it falls, the Earth is curving away from it, and so it never actually hits the Earth. And in that case, this cannonball would travel all the way around the Earth. Notice the entire time it's traveling, it's falling, but it's traveling forward so quickly that as it falls, the Earth curves away, and so it never actually strikes the Earth. So what this is saying is if you take the principle of inertia and you add to it the force of gravity, that gives you eventually an orbit of a projectile. Okay? So you can create an orbiting projectile by simply firing it fast enough and letting it fall toward the Earth, but never hit the Earth. That is precisely Newton's insight, and that is what he saw as an orbit around the Earth of, for example, the moon. So he thought of the moon as in continuous free fall toward the Earth. So here's the moon. It's falling toward the Earth, but because it's moving so quickly, it never actually hits the Earth, much like that cannonball fired horizontally never hits the Earth. So the moon is in this orbit around the Earth. It is literally falling the entire time. So if you were, let's suppose God were to put his hand in front of the moon and stop its forward motion, it would simply fall straight toward the Earth. But again, because it's moving so quickly, it orbits the Earth instead. Another way to think about this is if you consider, for example, the International Space Station. What's the International Space Station doing? Well, I'll draw a little picture here. Let's suppose this is a satellite or something like that. Well, it is literally falling toward the Earth the entire time, but because it's been fired or launched with enough horizontal velocity, it is able to orbit the Earth like this. Okay? That's the idea of an orbit. And so, if you've ever gone off of a diving board, when you jump off a high dive or a platform, sometimes you'll feel that feeling in your stomach as you're falling, right? Well, if you think about what's happening to the astronauts on the International Space Station, that would be how they feel all the time, because they are literally in free fall the entire time. So as they're orbiting the Earth, they're falling, but they never hit the Earth because they're traveling fast enough. They probably get used to that feeling, and so they don't think about it like jumping off of a high dive, but that's literally what's happening. Okay, so now that's kind of how Newton arrived at his universal law of gravitation, and so he's explaining the orbit of the moon around the Earth in terms of a gravitational attraction toward the Earth. Likewise, the Earth is orbiting the sun because of a gravitational attraction between the Earth and the sun. So this kind of analysis extends to the orbit of the planets around the sun. So if you have the sun right here, what's happening with the Earth? Well, the Earth is falling toward the sun, but because of its great speed, it's just orbiting the sun, and likewise with the other planets. Okay, so the problem that this universal law of gravity solves is it is able to account for the orbital motion of the Earth, Mars, Mercury, Venus, Jupiter, Saturn without having to resort to another kind of sphere on which it's riding in order to go around the sun. Okay, let me say one other thing about the work of Isaac Newton before I go on to Freidrich Bessel. At the end of his Principia, in one of his meditations, one of his scholia, once again, one of the things that Newton talks about is the distance to the stars. So if you look out at the stars at night, you will notice that some of the stars are brighter than others. Some are very dim, some are very bright. And the idea that was common throughout most of history was that the stars are affixed to a celestial sphere, right? Now, the ancients thought this huge celestial sphere was rotating around the Earth once per day. The more modern people, early moderns like Copernicus, thought that the sphere was sitting still and the Earth itself was spinning and going around the sun. But in any case, the idea was that all these stars were at the same distance from the Earth because they were affixed to this enormous celestial sphere. One of the things that Newton talks about, and he likely wasn't the only one thinking about this, but he says, well, it's not really clear whether the stars are all at the same distance from us or not. After all, if two stars look like they are different brightnesses, there could be two reasons for that. Either they could be at the same distance from us, but one of them is just intrinsically brighter than the other one, and that's why it looks brighter. Or perhaps they could be the exact same intrinsic brightness, and one could be much closer. The one that's much closer would appear brighter, the one that's farther away would appear dimmer. And really, by just looking at the stars from here on Earth, there's no way of knowing which of those two answers are correct, whether they're at the same distance and just one is intrinsically brighter and one is intrinsically dimmer, or they have the same brightness and at different distances from us. And he really provides no way of knowing which one is closer or not. The first time that anyone was ever able to measure the distance to a distant star was in the 1800s. And Freidrich Bessel was the one who measured the distance to 61 Cygni, which is one of the most nearby of the stars in our own galaxy. He did this in 1838. And what I want to do in my next lecture is talk a little bit about Freidrich Bessel's measurement of the distance to 61 Cygni using parallax. After having touched on the work of Newton and Bessel, then we will return to the work of Henrietta Leavitt and show how what she did fits into this broader context.